Forces always act in pairs. A force never acts alone. In this world, there are truly no examples where action and reaction do not occur. So you might say, I saw a girl I had a crush on at campus and gave her a wink but got no reaction, and then ask, isn't that an example where action and reaction don't apply? And if you ask that, you'd be correct. But that's because it's a matter of psychology. What we're learning here is Newtonian mechanics, the science of mechanics. Hello, this is Minsikhem from Minsikhem Academy. Today we will learn about Newton's third law, the action-reaction law. First, what is the action-reaction law? Students know this well. You already learned a lot about this in middle and high school, right? So, although I usually like Chinese characters, this time I prepared it in English, because it's more intuitive. We simply call them action and reaction. So the rule is, if there is an action, there must be a reaction. In terms of force, in Newtonian mechanics, if there is an action, there is a reaction. For example, with a person's hand on a friend's. If you hit the head like this, let's say you applied a force of 1,000 newtons, then it reacts maybe by screaming or saying, ah. But now, even as you apply a 1,000 newton force, your hand also experiences a 1,000 newton force in return. The magnitude of the forces is identical, and their directions are exact opposites. This is the law of action and reaction. If it's not 1,000 newtons but 10,000 newtons, you also receive a force of 10,000 newtons. Your hand would feel numb too. So to your friend, you could say, in the action-reaction law, hey, I'm hurt too. Hey, are you the only one hurt? I'm hurt too. You shouldn't keep hitting like that. The reason is, first of all, you shouldn't hit between friends. But if you do hit, why does your friend get hurt more than you do? It's because of the point of impact. Unless your friend's head is a rock, it's generally softer than your fist. Your fist or hand has bones, so it's harder. That's why it depends on the point of impact where the force is applied. Even with the same force, it matters where it hits. So when we fall on our butt or bump into something else, it hurts, right? Because even though it's the same force, it depends on the location. So in martial arts what is it? Boxing and similar activities also involve the same action and reaction forces, where the force is the same, but the opponent aims to hit a weaker spot. That's why combat sports exist. With just action and reaction, the magnitude of the force is the same, and both sides receive the same impact. However, because the location of the impact is different, it can be more painful or less painful. Got it? Then let's look at an example of the action-reaction law. Cheolsu and Younghee, these names come up a lot, right? What happens if Cheolsu and Younghee push each other on an ice rink? They move themselves like this. They exert force on each other in opposite directions like this. The magnitude of the force is the same. The force with which Cheolsu pushes Younghee and the force with which Younghee pushes Cheolsu are the same in magnitude. If we were to draw it, here, F Cheol Young, the force Cheolsu exerts on Younghee and the force Younghee exerts on Cheolsu are equal in magnitude. Because the magnitudes are the same, when you take the absolute value, it represents the magnitude, right? The magnitude in the vector is the same, but the direction is opposite, so they move in opposite directions. But how is it? They can move at different speeds. The reason is that if the magnitude is the same, for example, if it's 100 newtons, then according to F equals ma, if Cheolsu's mass is, for example, 100 kilograms, then with that 100 newtons, the acceleration would be 1. On the other hand, Younghee has the same 100 newtons, but if Younghee has a mass of 50 kilograms, the acceleration would be 2. And this value is for Cheolsu. Makes sense, right? So if you consider Cheolsu's movement in this direction as negative and in that direction as positive, Cheolsu's motion is now uniform acceleration with an acceleration of -1. Let's assume there is no friction. On ice without friction, this kind of uniform acceleration occurs. Younghee, on the other hand, moves with uniform acceleration in the right direction with this acceleration. Like this. By now, you're probably getting used to drawing graphs with me, right? You don't need to be perfectly precise just to understand that this is the kind of motion that occurs. It acts with force in the opposite direction like this. Next, the second one, you see the person running, right? This person running? There's also this running. It's not that the students are exerting force. The students are actually running due to the reaction. When running, if you look at the back foot, the heel, it's hitting the ground like this, the ground. Do you understand? Kicking the ground and then the ground's... The pushing reaction, this action is when the students hit the ground with their legs, the ground. Then, in reaction to that, opposite magnitude reaction. This is now the force of the ground pushing the student's feet. Got it? Because of that, they lift off. They jump and move forward slightly while in the air. Right, we can separate the vectors to graph their x and y components. This makes the running motion look like a series of jumps. So if you hit the ground hard at the right angle, that's how good runners do it. But just because we know that, it doesn't mean we can say, I know physics, so now I can run well. Just hitting the ground hard doesn't work. Got it? Truly skilled people don't do it with their heads. They already do it well by instinct. That's why being good at physics doesn't mean you're good at running. I run the 100 meters in 20 seconds. Got it? Okay, next. Here, a rocket. You might think a rocket propels itself by expelling fuel. That's not the case. It doesn't generate thrust on its own. Rather, by burning fuel and expelling hot gas downward, it's pushed upward by the opposite reaction force. Makes sense? So the rocket is pushing gas out in this direction, you see? In response to that explosive push, a reaction force of the exact same magnitude is generated in the opposite direction, and this is what allows the rocket to move forward. That's the reaction force we're talking about. Make sense? We can think that everything operates through action and reaction forces. Got it? Then what might not involve action and reaction? Action and reaction. I gave 3 examples earlier. Action-reaction, yes, surprisingly. There is no example where action and reaction do not apply. In other words, forces always act in pairs. A force has never acted alone. There is no place where the law of action and reaction does not hold. In fact, we found examples of action and reaction earlier. I gave examples of action and reaction, and earlier showed 3 examples. There are no examples in this world where action and reaction do not occur. If you find an example where action-reaction doesn't occur, let me know, because that would directly contradict the laws of physics. Action and reaction always exist. A force has never existed on its own. They always act in pairs. So what if you come to me and say, hey, I found an example where action-reaction doesn't apply? You might say, I saw a girl I had a crush on at campus and gave her a wink but got no reaction. And then you'd ask, isn't that a case where action-reaction doesn't apply? If you ask that, yes, it doesn't apply. But that's psychology. Psychology. What we're learning now is Newtonian mechanics, not something that connects with people's hearts. It's only applicable when a force is exerted, so a wink isn't a force, right? To some people, it might be a force, but when a physical force is applied, a reaction occurs in the opposite direction. It's not a psychological thing, got it? So in Newtonian mechanics, mechanics is force. Force. When a force is applied to an object, this is called action. Now, there's an object that receives the force, right? That object in turn exerts a force back on the original object that applied it. An identical force is exerted back. That's action-reaction. So, you see, force always exists in pairs. Then let's take a look at this example. All right, many students don't know this part well. If you draw the free body diagram incorrectly, you're going to mess up. Got it? So today, this action-reaction is... Conceptually, it is very important. When is it? It comes up next, but first let's take a look at this. These 4 forces, A, B, C, D. Let's find the reaction. Let's call this the action. Then let's find the reaction. Reaction. First, the gravity acting on the book. A book. This must be a book. This is a book and this is a desk, right? Then the gravity acts on the book. Then it's the Earth. The Earth is pulling this book, right? Then the reaction here is the force of the book pulling the Earth. Pulling force. Got it? It's the same. It's called an A prime. This is the force exerted by the Earth. Next, the force the book exerts on the desk. The force the book exerts on the desk. This is the book's color. Is it orange, yellow? Anyway, then the force the desk gives is B. So conversely, the desk supports the book. So the reaction is the desk supporting the book. This is the reaction. Right? Then the gravity acting on the desk. If this is the gravity acting on the desk, then the Earth also acts on the desk with a force in the opposite direction called C prime. The magnitude is the same, so it's the force of the desk pulling the Earth. The normal force that the desk exerts on the book. Wait, this is the same as the other one. This is the reaction force to B, right? Then the force that the desk gives to the book is the normal force, so conversely it would be the force the book exerts on the desk. That is, B and D are... It's exactly an action and reaction relationship, right? Between the two. The two are action and reaction. So there are problems like find the action and reaction here. Such problems won't appear on the exam, but it's really important when drawing free body diagrams. Got it? That's why I always write this down for students. Forces always act in pairs. Whenever there's an action, there's always a reaction. So there's never a situation where there's no opposing force. Understand? There are always forces, and there are people who say things like this. Okay, so I get that when I jump, the Earth pulls me back down. But you said I also pull the Earth, right? I also pull the Earth, so why doesn't the Earth come to me? It does. But look at F equals ma. F equals ma. For example, if a male student has a mass of 80 kilograms, even if the Earth pulls with a force of 10,000 newtons, it's actually 9.8. Rounding gravity g to 10, the force is only about 800 newtons. And while you do pull the Earth with that force, you have to remember its enormous mass. It's the Earth's mass times acceleration, so the Earth's mass is... It's enormous. Because of that, Earth's acceleration is almost zero. It's very small. So Earth doesn't move. I'm the one who moves and falls to Earth first, right? You understand, right? Now the last part is, where do we use the action-reaction law? This is important. In fact, for students, the conclusion is important. They might understand what's been explained so far, but where will they use it? Isn't this unnecessary? They might think this way. Right? Now let's define two things you need to know. I'll decide on the key points. The first thing is that when drawing a free body diagram, you should not draw the force you are exerting. This is important. Earlier, when asked to draw a free body diagram, many students couldn't do it. Got it? But if you learn how to draw a free body diagram with me next time, you will never make a mistake. That's important, understand? You must learn free body diagrams properly, as you'll be using them for the next 4 years. Even if you skip the videos on Newton's laws, this one is essential for solving exam problems. The next video will show you exactly how to do that, so be sure to watch it. If you understand the concept and learn how to draw free body diagrams, that knowledge will stick with you for a long time. Now, number 1. When drawing a free body diagram, do not draw the force you exert. Action and reaction apply to the free body diagram. Free body diagram. And do not draw the force you exert. Let's look at Cheolsu and Younghee. If Cheolsu and Younghee are there, the force that each exerts on the other is action and reaction. When drawing Younghee's free body diagram, you should only draw the force that Cheolsu exerts on her. That's why F equals ma. Here it would be Younghee. Since Younghee is moving, it would be Younghee's acceleration, right? Then this is the force Younghee exerts on Cheolsu. Do you understand? When you draw a free body diagram, we'll go into detail about this next time, okay? You do not draw the force of Cheolsu pushing Younghee here. You must never draw it. Many people get confused and make mistakes with this. Got it? You must never draw it. Even when you run, like when you run earlier, look, it's not about you doing it like this when you run. It's not about you hitting the ground. It's about the ground pushing you, and that's how you move. We need to move by using that reaction. Be careful with this. Understood? You might not understand it right now, but just try to understand. Applying it will be done next time, and as you solve practice problems, you'll gradually understand. Then action-reaction forces act on different free body diagrams. Here. You can't draw the force you exert, you can't draw it here. Not drawing the force of Cheolsu pushing Young-hee here like before, that's the first thing. And the second is, they act on each other. You have to draw them on each other. When Young-hee gives force to Cheolsu, it should be drawn on Cheolsu's free body diagram, and when Cheolsu gives force to Young-hee, it should be drawn on Young-hee's free body diagram. Got it? Each other's free body diagram. If there are two moving objects, you need to draw two free body diagrams. If there is one moving object, you will draw one free body diagram. Got it? However, when drawing a free body diagram, you should not draw the force you are applying, but rather the force in the direction of the reaction that comes from applying it to another object. Remember this well. Through this method, we will properly learn about free body diagrams next time. Good job.